most of the examples I'm going to give with vectors are going to be in 2 dimensions, so we can easily draw it, visualize it. But it can easily be translated into 3 dimensions as well. And this is going to be a tool for us to begin exploiting functions in a new form now by using vectors. So in the next chapter, and this isn't until the next chapter, but in chapter 13, what we could do is we could take those parametric functions that we had for x and y and place them in vector form. So now we have these functions sitting in these vector spots that would describe the x and y values of things, or x, y, and z values of things, and then now we can explore these curves in not just 2 dimensions as parametric equations, but 3 dimensions. We can call it parametric equations, or we can call it vector-valued functions. We're also going to use vectors as a tool, much like we use points. You know how we have input is x and output is y. Well, when we carry an input, when we start studying functions of several variables in chapter 14, we carry these inputs as a set of numbers, a set of points. So we can think about inputting a point, but we can also think about inputting a vector. And as we'll see here, the notation for vector and the notation for points can sometimes be interchanged. But there is one special thing about a vector, is that a vector has a specific, 2 specific properties. It has a specific direction and a specific magnitude. Have you guys heard that before? I forgot to prepare this. I usually have this ready. Now it's a commercial. Sorry.
I'm applying for a new film loan by the name of Vector. It's a mathematical term. Quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah! Check out the Piranodon! Oh yes! Fires live piranhas. Never seen one before. Now you have my adventure. You want a demonstration? Oh, ow! So difficult sometimes.
All right. All right. Well, if you didn't believe me about the direction and magnitude business, you should believe Vector himself. You can look at it as a line segment if you want, directed line segment. Direction. So we denote vectors with arrows. And when we draw an arrow, we think of what's important in this arrow. What's important in this arrow is that it has a specific direction that it's going towards and a magnitude, the length of the arrow. What that means is that if I have another vector with the same direction and same magnitude, regardless of where it is, it should still be the same vector. So these two vectors we would consider to be exactly the same, although one of them is in a different place from the other one. Okay? So that idea is not that big of a deal, but the question is, how are we going to know if two vectors are the same, and how we're going to work with them symbolically or even numerically, for that matter. So let's talk about resolving a vector. And for us, the best way to think about resolving a vector is think about your space that you're dealing with. Like I said, we're going to be looking at these vectors two-dimensionally, but we're going to also be able to look at things in 3 dimensions. So if we have a vector out somewhere, and then we had another vector out somewhere. It kind of looked close. To figure out whether these two vectors are the same, one of the things that we can do is we can what's called resolve the vector. And the way for us to resolve the vector is to take that vector and put it in standard form. So a vector in standard form would be that vector whose tail is at the origin. I guess I should talk about heads and tails too. So let's formalize a couple of other things here for a vector. The vector, you can look at the vector as having a starting point and an ending point. The starting point is called the tail, and the ending point is called the head. And then if your tail is sitting at the origin, then your vector is what's called in standard position. So a vector in standard position just means the tail is sitting at the origin. And what that means now is that we can look at, if your vector is in standard position, the head, or where the vector is pointing to, is that it's pointing to a point and let's just call it for now A comma B. So if your vector is in standard position at 0, 0, and then your point is at a point, your vector's head is at the point A comma B, then that means we can call that vector AB. So the vector V let's call vector v. By the way, another notation for vectors is that if you want to use a letter to represent a vector, the book uses boldface. And so when we're writing things, doing a boldface is kind of difficult to do. So for us, we'll put an arrow on top of your vector notation. And that little arrow says that this is a vector. And then I've always been kind of lenient on the idea that the vectors can be written as a point. So a lot of times I use parentheses for vectors, but it's also sometimes good to denote vectors with a different sort of bracket. And so we will use these, I don't know what to call them. They don't have a name. We'll use these brackets to denote. Some people call them alligator brackets, greater than or less than brackets. And some people don't like to use this because this notation in math symbolizes this thing called an inner product. And so using this bracket is not what math people tend to use. The what? Yeah, and there's also the using the standard unit vectors that we'll talk about in a few minutes. So this is one way to denote vectors. Okay. And if you've taken physics, this is going to be really, really boring today. So just try to stay awake. Okay. So that's one way to think about resolving a vector. So now, say we had another vector over here. And let's give it actual values like, I don't know, -2, 1, and would be -3 maybe, 3. So these are the actual points of where the tail and head are. So we can think about bringing us down back to the origin. To quote, resolve our vector. But instead of physically doing that or graphically doing that, can we somehow find a way to resolve the vector without moving it around like this? And how would we do that? Yeah?
I was just kind of thinking about it. I'm moving left 1 unit and up 2. So in terms of like a slope, kind of establishing that it's -1, 2 vector, but it's up and to the left. I don't know if that's like a valid explanation.
Well, I think it's valid. Well, the final answer is correct. Explanation could use some polishing. So what did you do? You just subtracted, right? Yeah. So basically, that's what that's the short end of it. What we want to do to resolve the vector is basically subtract the points, head minus the tail. And we could think about the head as, -3, 3. The tail would be -2, 1. And we can think about it as just, subtracting points is kind of weird to think about, but if we look at the points as vectors anyways, we're going to get into this a little bit later on too. So -3 minus -2 is -1, and 3 minus 1 is 2. So we must be at this point. -1, 2. So we can call that the vector -1, 2, either use parentheses or use those brackets. Okay? All right. So as tools, we can look at this as like the basic building blocks of the new thing that we're studying, new thing in higher dimension that we're studying. So as tools, we want to develop the usual binary operation that we learned when we were back in, I don't know, kindergarten, when you were learning how to add things. So your tools were numbers, and then you learn how to add, you learn how to subtract, eventually you learn how to multiply. So we're going to do things like that with vectors. We're going to add, subtract, and multiply these vectors. Let's see what we get. So as we're looking at these vectors, though, we have to assume that these vectors are taking on something different from the first set of tools that we were dealing with, which were numbers. So these don't look like regular numbers anymore. You know, these carry a direction and a magnitude. Numbers just are numbers for us, right? So we want to make a difference. So vectors are going to be called vectors. But numbers are going to be called something different now. We're going to refer to numbers as scalars. So when we begin looking at a lot of vector terms and ideas, we're going to need to distinguish a vector from a scalar from a vector. Okay. So let's throw that out there. And then now let's go back to our adding and subtracting and see what the geometry looks like and all that stuff. So vector addition involves, geometrically, we can view vector addition in kind of a nice way. If we have a vector that we'll call the first vector v, and then we'll call the second vector u. So to make this addition, v plus u, geometrically, what we're doing is we're kind of tacking on, starting with v, we're going to tack on the vector u from its head. So we're going to take the vector v, or the other vector u, the thing that we're adding, and then we'll put it at the head. We'll put its tail at the head of where the vector v ended, and then what we will get is a new vector starting from the tail of v going to the head of u after you have added it. They're not quite there. There it goes. So that vector is the new vector. And vector addition is commutative, which means you can switch the order. So visually, you can think about V and U being added, where V goes first and then U goes second. Or if you switch the order, it actually, you would complete this sort of parallelogram business to have your drawing. Symbolically or numerically, when you actually do this, it's quite simple. It's just adding component-wise. So let's set V equal to some random set of numbers. V is equal to 2, -1 maybe, and then let's set U equal to 7, 3. So when you add them, you're going to add component-wise, so it'll be 2 + 7, and then -1 + 3. (9, 2), and so that would be your result. Okay, pretty straightforward. Seems like it. So now we can essentially take the same picture and then look at subtraction, and it'll look slightly different. So why don't I take a picture of this and do subtraction page. So let me move a couple of things. So this time in vector subtraction, when we're subtracting two vectors, what we could do is we can think about those vectors in standard position. And those vectors, if they were in standard position, they would represent the points where their heads are pointing, right? And so if we have a head pointing here and a head pointing here, and then we have V, the head of V minus the head of U, the head of V minus the head of U, we can think about that as kind of like that subtraction that we did to resolve the vector. We can think about that as head minus tail. What does that mean? What am I talking about? So I think what I'm trying to say is that the new vector subtraction that you would get would be this vector whose head is at the head of U, or V, that's the first vector, and whose tail is at the head of the second vector. So if we thought about this as a head minus tail construction, the new vector that we're looking at will have its head at the head of that first vector, V, and will have its tail at the head of the second vector, U. Yeah?
Say if we swap the order and by which we subtracted, would it make the vector turn around the other direction? Like the tail would start at B?
Yes. Yes, so if we switch to order u minus v, then that's a different vector because it's going in the opposite direction. That's correct. So if we do the subtraction here, where v is equal to 2, comma, negative 1, and u is equal to 7, comma, 3, then the subtraction, the numerical perspective of this is that subtraction will be done component-wise. So we have a 2 minus 7, negative 5, negative 1 minus 3, negative 4, and so our new vector is going to be this. To follow up on Matt's comment about switching the order, if you did switch the order, numerically, you would have 7 minus 2, comma, 3 minus negative 1, which is going to be a 5, comma, 4. And you see that that is just exactly the same vector, except there's a negative in front of it. And if we look at that, geometrically, it's going to be the exact same vector as the first one, except since it's going negative, it's going to go in the opposite direction. Okay? Which will bring us to our first type of multiplication with these vectors. Any questions so far? Okay. Maybe we should make a point that this is u minus v, and this is v minus u. Okay. All right, so we're able to add vectors and subtract vectors, and the computation is pretty straightforward. You do it by component, component by component. Geometrically, I didn't redraw the parallelogram, but one can think about this as the addition and subtraction of vectors are both diagonals of the parallelogram. So if we take a look at the first picture, this is the diagonal going from tail to the new head of the parallelogram, and then the subtraction is the other diagonal for the parallelogram. So you can find that interesting. There's a lot of geometry that you can construct with that. Now we're going to move on. Okay? All right. The next simple operation we can make with vectors is multiplication, but multiplying two vectors together is going to be a little tricky. And so we're going to save that for last. There's another multiplication that we're going to take a look at, and that's multiplying a vector with a scalar. And this is called scalar multiplication. So let's say we have a vector v. A scalar multiplication takes a number, scalar, and then multiplies it with a vector. So let's take, as an example, 2v. What's 2v going to look like? Now, numerically, the scalar multiplication is like a distribution of the scalar onto the different components. In fact, let's probably, what was v equal to in the previous page? 2, negative 1. So the new vector 2v is going to be 2 times 2 comma negative 1. And what we could do is we can think about this as distributing the scalar to each of the components. So this is going to be 4 comma negative 2. So 4 comma negative 2 is going to be your new vector. But how's that going to look like geometrically? Geometrically, this just turns out to be this vector in the same direction, but twice as long. So what you're kind of doing here is you're multiplying its magnitude. So you're multiplying its magnitude. Okay? So if you do it 3 times, then it'll be 3 times as long. If you do it a negative 1 or negative 2 times, let's do negative 1. Negative v is making it go the opposite direction, and that's exactly what's going to happen. It's going to make it go the opposite direction. So we can think about a negative v vector as going in the same direction as v, or at least parallel to v. I guess saying the same direction doesn't make sense anymore. But in the same direction, or in the same parallel plane or parallel line, but going in the exact opposite direction. There it goes. Okay. All right. So let's say I had my vector 2 comma negative 1, and I want a vector going in the same direction, but I want it to specifically have magnitude of a magnitude 1 or something. Magnitude. Magnitude. Let's talk about magnitude. Let's find the magnitude of v, which is 2, negative 1. Now imagine this being a vector in standard position, and you want to find the length of this vector. So magnitude is length. You can think about it as length. There's a g in there somewhere. So if you imagine this as a point, a vector in standard position at the origin, then you can try to find the magnitude by just finding the distance between the 2 points, right? Like a distance formula. So that's essentially what we're going to do is we're going to pretend that the second point is 0, 0 in standard position. So we have a 2 minus 0 squared and then negative 1 minus 0. I mean, you can also use Pythagorean's theorem or whatever. But in any case, the notation for this that we'll use is we'll use a double bar. And sometimes you'll see books use just a single bar. What do you think of when you think of the single bar? Absolute value. We'll come back to that idea in a minute. But to find the magnitude of a vector, what you want to do is you basically square each component, add them, and then take the square root. So if you have a picture in your head of this vector, take out the arrowness of it, and then find the length of this by using triangle and Pythagorean's theorem or something like that. In any case, whatever geometry you use to find this length, you'll come out with the same result. And this is going to be some positive value. So it's basically the distance from the head to the tail. And if the tail, if it's in standard position, it's basically the distance from the point to 0, 0, or to the origin. Okay? Let's go back to the absolute value. What is the absolute value? How is absolute value defined? Yeah?
It's defined as, I guess you would say it's a number that's basically a distance from 0, 0.
It's basically the absolute value that we apply on scalars, on numbers, is really, the definition says that it's the distance from that point to 0. So if you're on the right side of your number line, then it's a positive number, the distance is positive. If you're on the left side of your number line, then it's a negative number, but you're still just measuring the distance, so you ignore the negative and say it's positive. Right? Another way to think about this is that for scalars, absolute value of a number is equal to the square root of x squared. I mean, look at the number as if it was just on the x-axis in 2 dimensions. Then the y is going to be 0 anyway, so 0 minus 0, you're not including 0. But you can think about it as this, the square root of x squared, which is going to be positive of whatever it was. And the order of this is important. It's the squared is being done first, and then you're going to take the square root. By squaring any number, you're going to make it positive, and then you take the square root, it's going to be positive. Okay, so there's no issues with weird negative imaginary numbers in this case. So sometimes they use this idea of an absolute value for the magnitude because it means the same thing for scalars and for vectors. So sometimes if I forget the double bar, I'm excused. So the magnitude of this particular vector looks like it's going to be square root of 5. So this vector, which really is, should we actually make it 2, 1? Two, 1, negative 1. Guess this is actually how the vector should look like. I'm going to make it a little bit longer. And I'm going to put it in a frame of the xy plane. Sometimes we might be concerned about the vector, the direction of the vector itself, and not necessarily its magnitude. And so whenever that happens, we usually want that vector, the same vector, not the same vector, but the vector going in the same direction, but with unit length. And so there's going to be some sort of need sometime in the future to find a vector of unit length. And so we should know how to do that. So if this is your vector, we can use our scaling properties, scalar multiplication, to scale this so that it has unit length. At this point, we know that its magnitude is 5, or square root of 5. So the question is, can we multiply this vector by something so that it will have unit length? It would have length 1. I'm assuming 1 is a little bit shorter than that. So now the question is, can we find this vector so that its length, let's call this new vector u, so that the magnitude of u is equal to 1. Any ideas how to get that? Yeah? So if you divide the vector by its magnitude, multiply it by the reciprocal, then that'll work. So u will be equal to the vector v divided by the magnitude of v. So this will always guarantee that you will get a unit vector. So this vector, u, will be going in the same direction as v, but will have unit length. And just for an example, we'll use these numbers, but it'll work in general if you use generic numbers instead of using 2, -1 like we're using. You can use a, comma b, and then go through the same process. That's how math works, by the way. You know, you make it arbitrary, like u and b, or a and b, and then you do the work, and then you'll get the same results. Yeah.
Why do we want to put it
because unit vectors because the magnitude is 1, they're easier to deal with. When your magnitude is larger, sometimes you're just interested in the direction, and having a strange magnitude might complicate things. And you know, sometimes size really doesn't matter. So we have 2, -1. If we divide each component by square root of 5, we get 2 over root 5 minus 1 over root 5. And just to check, and you don't have to do this all the time, if we want to find the magnitude of this, we're going to take the square root of the first component squared, add it to the second component squared, and you'll see that this is equal to 1. Okay. So going along the same lines, or how about going along the same direction, if you want a vector of a specific length, let's say I know that I have to hit this target over here, and I know that the vector v will be going in the same direction for me to be able to hit this target. Right? But I want a vector that has length, let's say, 7. So now the question is, I want to use my vector v pointing at this target to reach that target with one vector. So I basically want to look at my vector v, and I want to scale it so that it has length 7. So the question is, what do I do? What happens if I multiply by 7? Then I'll have 7 times square root of 5. That's way too big. Right? So if you want a vector going in the same direction as another vector with a specific length, what do you need to do? Make it into a unit vector first. Right? Once you make it into a unit vector, then scaling it to exactly what you want it to scale would do the trick. So if you take this, you divide by its magnitude, and then you scale it, then you're going to get that new vector that you want. So first, make into a unit vector then scale appropriately. Okay? So whatever vector we got last time, if you just multiply this unit vector by 7, this is going to go exactly 7 units, and then you're going to have magnitude 7. And that's what you want. Okay? Pretty cool, huh? Not boring?
What do you mean? Math is great.
Well, half of you guys are taking physics and you know all about vectors already, so. All right, let's do one more physics-like thing. Let's do more with the idea of resolving vectors. Sometimes your vector might be given to you not by the components, because then that would be way too easy, but rather they would be given to you with a magnitude and a direction. I mean, after all, vectors are things with magnitude and direction. Sometimes the direction is given by an angle, and the magnitude is given by whatever the magnitude is given by. So, given a magnitude, and angle of inclination, let's try to resolve the vector. Now, if we look at this vector with the magnitude and the angle of inclination already at the origin 0, 0, then all we need to do is find out this value over here, the point of the head of the vector. all we really need is trig, right? So we can think about the pieces that we want. So the x component will be the side over here. The y component would be the opposite side. And then now we got flashbacks to trig. We got the hypotenuse as a scalar. The magnitude, by the way, is a scalar value. It's a number, positive number. So that can stand as our hypotenuse. And so your vector v can be given as the magnitude times cosine theta. And cosine adjacent over hypotenuse is a relationship. And then we have the opposite side is the y value times sine theta. Okay? So this will become important for us when we start studying these as functions, vector functions, and then we're going to start studying the motion of these things. Again, if you've taken physics, I think this is in 250, this is a kinetic motion thing. These are the formulas that's required for you to figure out a body moving with gravity imposing on it. And we'll do a little bit of that later. Okay. All right. We have a couple of other vectors to look at. Oh, maybe I should call the standard vectors. Standard unit vectors. Sorry. So after studying or knowing about addition and subtraction and scalar multiplication, we can now take a look at the standard unit vectors. And again, just living in 2D right now, there's two important vectors here on the xy plane. And those two vectors are the vectors that are moving from the origin up along the x-axis and then, up along the y-axis. And we could be specific about this. So the vector from the origin to the point 1, 0 is a special unit vector and is denoted by I, the I vector, or some people put hats, arrows. Okay.
So if you have,
that means it's a unit vector. Now, this can also live in 3 dimensions, and what's special about these vectors being standard unit vectors is that not only are they unit vectors, but they're perpendicular to each other. So the fact that they're perpendicular to each other is important. And if you're in 2 dimensions like we are in, then there's only 2 vectors that are perpendicular to each other that could be standard unit vectors. If you're in 3 dimensions, then you're going to have 3 standard unit vectors. And they're called the I vector, the J vector, much like in 2 dimensions, but now there's a K vector. When you go to 3D. So what this allows us to do is express, it allows us to express any other vector as a, linear algebra, as a linear combination of these standard basis vectors. So let's take that vector v that we had a while ago, or let's take another vector. If we imagine taking this vector apart, and further taking it apart, so in a way I kind of use backwards distribution or splitting this up. What we have is 0, 1, or 1, 0, which is I, and then we have 0, 1, which is J. And so now we can think about writing any vector as a linear combination of I's, J's, or in 3 dimensions, I, J's, and K's. So sometimes you'll see the vectors written like this, and it's not to be taken for granted that they represent these I's and J's are not placeholders or not like the parentheses. They are actual vectors. And what you're doing here is a linear combination of vectors. By doing the addition and scalar multiplication of these vectors, you're expanding it to the I's and J's. Okay? All right, one more thing about vectors. Now, we've been talking of vectors in 2 dimensions, and then all of a sudden I got into 3 dimensions. But really, vectors exist in higher dimensions. So I always like to make an example of this. A vector is really just a collection of numbers. And it doesn't really matter what we have in there. It'd just be a collection of numbers, and that can be represented as a vector. And when appropriate, we can continue to think about addition, subtraction, scalar multiplication, and then these other things that we're going to do to the vectors, like the dot product and the cross product, which we'll talk about tomorrow. We can do these things, most of them, to vectors in higher dimensions as well. Okay? And the really prime example I like to use for vectors in higher dimensions is that the vectors can represent your grades. So, for example, when I calculate your grades include homework as a category. It includes quizzes, tests, labs, final. that's a 0. So each person can be assigned a vector with their average homework scores, quiz scores, test scores, labs, and the final exam score. Okay? Doesn't really make sense to add things. I mean, it could make sense to scalar multiply them. You can multiply somebody's vector and scalar multiply it. But one of the operations that we'll do is called a dot product. And that dot product is exactly what I use to calculate your grades with the vectors. So the unfortunate thing about vectors of higher dimensions past 3 is that you can't visualize it, because you can't visualize things that are larger than 3 dimensions. We are 3-dimensional beings, people, and so we can visualize 1 dimension, 2 dimension, 3 dimension, but we can't go past that. So if you're a 4-dimensional person, then you can do that, but you can't do that.
If you rotated, you would, if you rotated 90 degrees, then you would, then you would look like an entirely different 3-dimensional.
Yeah, probably. So the idea is that if you were in 2 dimensions, I think it's better to try to imagine what higher dimensions are if we put ourselves in a lower dimension. And maybe we'll think about doing that tomorrow. All right. Now you guys know all about vectors. Next time we'll cross them and dot them.
This. So what would we do? We have, it would be square root 5 over.
That would be 7 over square root of 5. And then you would multiply 2 comma negative 1 by 7 over root 5. And then it'll be a new vector in the same direction, but if you were to compute its magnitude, it'll be 7.
Oh, okay.
Yeah.
Oh, okay. Great. Thank you.
Just confirm we're ahead of day now? Because today we're supposed to finish 2.1. So tomorrow we're doing cross products? Or no, sorry, dot products?
Are we ahead? We're not ahead.
Yeah. That's good. So today was supposed to be
Oh,
2.2,
good.
So I think
Yeah.
we are ahead of day.
Yeah, good. That's always good because,
Helps with the homework. More time for it.
yeah, we are ahead. Okay.
So yeah, we are ahead. Let's double check out the credits.
What?
So we are ahead.
Yeah. Hi, Jocelyn.
I was just confused about one thing. So it's 2 should be here, not here.
Yeah.
It's on the other way.
Put a negative there. Should have told me that earlier in class.